Okay, well, hello again. We're going to start this one. It will go into example B very shortly, but I want to first take a note on the inverse of a relation and just write down this definition if you haven't already, so that you have a formal definition of what it means to take the inverse of a relation. So you get the inverse of a relation by exchanging the x and y coordinate points. I'm going to abbreviate coordinate there. Coordinate points, like we saw in that first example, or you can also get it by exchanging x and y variables in the equation. So I'm sorry this looks like a little kindergartner wrote this, but I'm still getting used to this. So either way, you have the formal definition. I'm just going to move on into example B. If you need to go back to this, pause it or rewind, whatever you need to do, but we'll move on here. So example B says, or asks us rather, to find the composition of this function with its inverse. So the function they're giving us is f of x equals 4 minus 3x. To find a composition of a function, we need two different functions, one to plug into another. Well, if they want it to find us with the inverse, then we're going to need to find the inverse of the function first. So find inverse first. And instead of making a list, a table, and doing a bunch of coordinates, and then flipping them and then rewriting the equation, we can use the second half of that definition where it said we can exchange the x and y variables. So I have the original equation as f of x equals 4 minus 3x. And they want us to exchange x and y. The problem is I don't have a y. So you have to remember that f of x is y in disguise. We just got fancy and started calling it f of x. So it's really y equals 4 minus 3x. So this is still the original equation. So in order to do the first step, we have to change this. We have to switch x and y. So switch x and y. So instead of y equals, I'm going to have x equals. And instead of 4 minus 3x, I'm going to have 4 minus 3y. Fairly simple first step. Now the next part, and that's just to solve for y. Because when we write equations, we like them to say y equals. So solve for y. And I'm just going to move this up over to the side here. So I have x equals 4 minus 3y. So to start to solve for y, I undo my order of operations, so I'm going to subtract 4 from both sides. So this becomes x minus 4 equals negative 3y. And then I simply divide divide by negative 3 on both sides to get y alone. So I end up with y equals x minus 4 over negative 3. And this is the inverse function here. Okay, can you tell I found some colors? I'm very excited about that. So we have our original function, f of x equals 4 minus 3x. Now I've found the inverse, so now I can start to compose those together. So let me erase some of this here. And again, if I'm going too fast, it's the beauty of this screencast is that you can stop, pause, rewind, whatever you need to do, re-listen to it so that you can get all the notes down that you need. Okay, so here we have the original function and the inverse. And the way we write the inverse is we notate it with a negative 1 in between the f or the g or the h or whatever letter we happen to have there and the x. And that means the inverse function. So this is x minus 4 divided by negative 3. So that's our inverse function there. They're asking us to find the composition of the function. So in order to find a composition, we have to plug one function into the other. So I could do the original function and then plug the inverse function into that. Or I could do the inverse function and plug the original function into that. Now, if you remember, compositions of functions, order is supposed to matter. You're not supposed to be able to do these differently or set them up differently and get the same answer. But this is going to come out a little bit different because we're using the function and its inverse. So let's check it out. So the first one's telling me to put the inverse into the original function. So I'm going to have f of the inverse is going to get put into the original function here. So this whole thing is going to go in here for x. So I'm going to have 4 minus 3 times, and then I have this whole thing getting put in here, x minus 4 over negative 3. So it replaces this x here with this whole thing here. Now I need to solve this. So if I start looking what I have here, I have 4 minus 3 times, and I have this whole setup over here. If I multiply negative 3, if I multiply this negative 3, and then I into these parentheses, and then I divide by negative 3, what actually happens? Well, these guys cancel, leaving me with 4 plus is positive x minus 4. And 4 minus 4, those are gone, leaving me with just x. So, what did I just find out? Well, I just found out that if I do this composition here, I get just a plain old x. Well, what happens if I did it in reverse? What if I put the original function into the inverse? Let's see. So now I have the inverse, and I'm putting in the original, 4 minus 3x. So that is going to go into x minus 4 over negative 3. So this whole thing is going to go in for x in that case right there. So we would have this 4 minus 3x and then minus 4, so here's the function that went in for this x here, over negative 3. Well, again, we have this 4 minus 4, which cancels, leaving me with negative 3x over negative 3, and the negative 3's cancel, leaving me with, again, just my x. So with inverse functions, forwards or backwards, plugging the inverse into the original or the original into the inverse, it doesn't make a difference. We get x both times. This is a really important concept that if you do the composition of a function with its inverse, you always get x. So to just finish off here, let's take that last note. Any composition of a function with its inverse equals x. And we can do just a couple of examples just to show you what I'm talking about. So if we have, for example, f negative 1 of f of x, we just saw that this is going to equal x. If you have g of g, the inverse of x, you're going to get x. And the same thing applies. So what if you had f of the inverse of f, but instead of x, let's say you have it of 6. Well, guess what's going to happen? You're going to get 6. So whatever number or variable is inside these parentheses when you have a function and its inverse, whether the inverse is outside or inside, you always get whatever that is there, whether it's an x or a number or a y or an L or any letter or number, you always get that out on the other side. So hopefully you took pretty good notes, and I will see you in class.